First, I wanted to thank Texas Instruments for providing us with such a great venue. Also, I would like to thank Signal Processing Society for co-sponsoring the event and publicizing the event. So I am the chair of the CIS SCV chapter. Amy Kulkarni in the back, he's the vice chair. Rajas Varahad Rajan is the secretary. He's in the back. And Priscilla Chen is the treasurer. She's standing there. Thank you all. So we will have a call for nominations for the 2018 officers. So if you are interested to volunteer for the officer position, please send me an email, and we will have an election in the next event, which is in December 4th. Also, if you just want to volunteer, don't want to be involved in heavier stuff, just you can volunteer. Just again, send me an email. So the next event will be deep learning in biomedicine and genomics. Speaker is Mark DePristo, head of deep learning for genetics and genomics at Google. It is on December 4th, Monday, the same time. Also, we will have a symposium, November 16 and 17, Artificial Intelligence Symposium. I think my Pavel, he can give you more information.
Good evening, everyone. My name is Pavel. I'm the vice chair for the Signal Processing Society, and we will be having the Artificial Intelligence Symposium this month on the November 16th and November 17th. It will be at Intel, and it will be 2 days of discussions and lectures and panels on artificial intelligence. So you can find out more by going to the Signal Processing Society website and looking at the event there. How do I switch slide? Yes. So the tickets are selling out quickly right now. We're almost at capacity, so if you want to attend, you should probably go pretty quickly. We have discounts available, as you can see here, for IEEE non-members, members, and the registration fees are $3.99 for regular price and $1.91 for members. Thank you. That's what I have.
Thank you. So just a quick note that because of the TI security rules, we have to leave the building before 8:45. So we try to close the event by 8:30. And if you have questions, you can ask during the talk. So the talk today is, the title is Learning with Limited Supervision. Speaker is Professor Stefano Ermon. He is the currently assistant professor in the Department of Computer Science at Stanford University, where he is affiliated with the Artificial Intelligence Lab. He completed his PhD in computer science at Cornell in 2015. His research interests include techniques for scalable and accurate inference in graphical models, large-scale combinatorial optimization, robust decision-making under uncertainty, and is motivated by a range of applications, in particular ones in the emerging field of computational sustainability. Stefano's research has won several awards, including 3 Best Paper Awards, World Bank Big Data Innovation Challenge, and was selected by Scientific American as one of the 10 world-changing ideas in 2016. He's a recipient of the Sony Faculty Innovation Award and NSF Career Award. Please welcome Professor Ermon.
Thanks for the introduction. It's a pleasure to be here. And today I'll be talking about my work on learning with limited supervision. Let's see if the slides can play. Do I need to do anything? Doesn't show. Showing here. Yeah, perfect. All right. Yeah. So as Meron said, I'm happy to take questions at any point. As you've probably heard, the last few years there's been really a lot of progress in artificial intelligence. It's really an exciting time to be working in this field, especially in fields like computer vision, where we've been able to build systems that are even beating humans at problems like object recognition on ImageNet. You see here that in the last 4 or 5 years, it's been really an enormous amount of progress in that space. Lots of progress in machine translation, speech recognition. There's been major breakthroughs in game playing with the DeepMind's AlphaGo system that managed to beat the very best world players at the ancient game of Go. And really, there are 3 main technical components that enabled all these advances. The first one is the availability of very high capacity models, very deep neural networks with hundreds of millions, billions of parameters. The availability of new hardware, especially GPU devices that allow us to train these models relatively quickly. But especially the key thing that you really need to get these kind of amazing results is a lot of labeled data. These models have very high capacity. You can feed them, you can train them to solve complex tasks, but you need a lot of labeled examples in order to do that. And so labeling data is really the bottleneck these days to get machine learning to work on some new applications. And so, you can really think of training data as the new oil these days. And so what this means is that, if you try to apply these kind of techniques to settings like physical sciences or development applications that are kind of the topics that I care about, you cannot just apply these kind of deep learning techniques out of the box. Now, on the positive side, even though labels are expensive to get, we do have access to a lot of unlabeled data in digital form. If you just go on the internet, you can get a ton of images, you can get a lot of videos on YouTube, on Twitter and other social media websites. You can get a lot of text data. If you're interested in applications of machine learning to the environment, to development issues, there is a lot of very interesting data that's becoming available from remote sensing, from satellites that take very high resolution images of the Earth every day. And really the challenge is, what do you do with all this unlabeled data? And the challenge is the problem of unsupervised learning. It's clear that there is a lot of information in all of this data, and the question is, how do we actually make use of it? Right? And so one general technique that I think is very promising, and it's quite powerful to think about these kind of settings where you have data, but you don't have necessarily labels. Maybe you have images, but you don't know, anything about what they actually represent. And you would still like to somehow make use of this and try to understand what all these images have in common, like that there is a person, and that a person has 2 eyes, and that there are different genders. You would like to somehow be able to understand the structure of the data in an unsupervised way, just by looking at the images. And so the idea of doing probabilistic modeling and doing generative modeling is that we would like to come up with a probability distribution over images. And this probability distribution should capture the structure of the data. So, and what this means is that it should be assigning high probability to images. So think of them as sequences of bytes that look like the face of a person. You should assign low probability to things that don't look like the images you've trained the model on. And so that essentially what it means is that if you were to draw samples from this probability distribution, you should be able to get new images that kind of look like the ones you've trained the system on. And intuitively, if you are able to solve this task, then it means that you've kind of understood the structure of the data that you're dealing with. And therefore, it turns out that you can use this kind of object, this kind of probability distributions, to solve a lot of interesting tasks. So here's another example of what you can do if you're able to learn such a probability distribution. This is a paper that we have upcoming at NIBS, where we essentially try to learn how to set up a Markov chain that explores this very high-dimensional space of images. And it's using as guidance such a probability distribution that kind of assigns high probability to images that look like faces. And you can see how it's traversing the manifold, it's moving around different modes of the probability distribution, and it's kind of has understood the structure, the high-level structure of these images. So just to move on, there are several applications of these kind of models. One is to just generate samples. Among these images, can you guess which ones are real and which ones are fake? Which one? Sure is fake, okay. So some of these images are fake, some are real. A2 is fake. C3. Yeah, it turns out that they're actually all fake. So, you know, it's not perfect. Like if you look closely, you can find artifacts. It's not perfect yet, but it's doing a pretty good job, right? It can fool, if you just look quickly, you don't pay too much attention, it might actually be able to fool you. Another thing you can do is you can essentially impute missing data. Let's say that I give you a partial image, like I only give you the central part, the central crop of the image, just corresponding to the eyes of the person. Then you can basically condition on the fact that you know the value of those pixels, and you can ask and you can sample from the probability distribution corresponding to the other pixels, given that you know the value of the pixels in the middle. And you can see that it's doing a good job at capturing the uncertainty that you have in the data. In this case, it's producing two samples. They have the same eyes, but they correspond to a male and a female, right? So it's capturing the fact that there is variation in the data, that there is uncertainty, and you really want to be able to, and the fact that you're dealing with a probabilistic model lets you handle these kind of situations very, very nicely. It's not only restricted to images. This is some other work that we have where we try to do this kind of, try to apply these kind of ideas to audio signals. The idea is that there's plenty of voice data online. You can just download a lot of it, and you can train a model that will essentially try to assign high probability to sounds that sound like human voices. And then you can basically play the same trick. You can say, I'm going to give you a subsampled version of the signal. I'm going to throw away some of the data. I'm going to give you some signal that is basically has the same quality of the voice that we have on your cell phones. And then you can ask, now try to fill in the missing values. Try to upsample it, essentially. And now let's see whether this works, because we haven't tried it, but okay, this is not working. I guess the audio is not working, but you can check it out on my website. It works quite well. It's able to reconstruct a lot of the high-frequency components of the signal that are missing, because it kind of recognizes, it learns basically what human voices sound like. It learns to recognize different phonemes, and it's able to do a really, really good job at reconstructing signals. The other, perhaps more exciting application of these techniques is that you not only can apply them to kind of static data, like a static image or a static audio signal, but you can apply them to more complex data streams. And in particular, we've been using these kind of models to do imitation learning, where the idea is that you can observe a person perform a certain task that you care about, like say driving a car in this driving simulator. Okay, this one is not working either. me see if I can. What should I click to? Okay, it's back online. Okay, now it's showing on my computer, but okay. Should I close this? Let's see if the sound plays, maybe.
One is investment, one is reform.
Okay, this is the low resolution. Let's see if we can.
One is investment, one is reform.
So you can see the difference. This is the low resolution.
One is investment, one is reform.
And then you can fit it into the model, which is basically doing the same thing as here of trying to fill in the missing values that you don't know.
One is investment, one is reform.
And it sounds much more. Yeah, sorry. I think that you need headphones to hear it well.
One is investment, one is reform.
This is I think we upsampled it by a factor of 4.
One is investment, one is reform.
I think this is either by 4 or 8. You can find them on my website, and with a headphone, it sounds much better. The other thing you can do, as I was saying, is that you can try to do imitation learning. Here the idea is that you might observe a human or an expert kind of perform a task, like driving a car in this driving simulator. Not playing again. It was playing on my top right. Do I click here? Nope. Okay, looks like the videos are not playing. Somehow they work on my screen, but not on that one. That's something we still haven't figured out how to make work. But anyways, the idea here is that you can try to learn how to imitate this behavior, and you can learn how to drive a car by essentially generating sequences of states and actions that imitate a human behavior in a complex environment. And unfortunately, it's very hard to understand how that works without seeing. Somehow it's not playing. Does it work? before. Okay, it's working. All right, sorry about that. So you can see here the idea is that you can train the system by showing demonstrations of how the human is actually driving this car in this game from the 90s. And the goal is to learn how to imitate this behavior by producing sequences of states and actions that sort of like look like the ones you have in your training data, right? We'll see whether you need the images or you need more, but yeah, we can actually do it just purely from the images, it turns out. Yeah. So the kind of general mathematical formulation that we're going to use is one of a latent variable model. The idea is that we get to see some variable x, which could be, say, an image, so a bunch of pixel values. And the idea is that there's going to be some latent variables that kind of explain the variation that we see in these images. But these latent variables z are something that we don't get to observe. The only thing you get to see are the x, and then there is some corresponding z that is kind of like describing this variation that you actually see in the data. So it could be like the cartoon picture, could be something that looks like this. There is some latent variable capturing whether or not this is a male or a female, something corresponding to hair color, eye color, pose, things like that. And the hope is to be able to learn a model where these latent variables, where you basically, even though you don't know the value of z, you can still try to learn a probabilistic model by essentially trying to integrate out the uncertainty, right? And if you could do that, then you could do some interesting things like this, because if you have some kind of meaningful latent structure in your data, what you can do is you can fix the value of some of these latent variables, and you can produce samples from the model like we were doing before, but you can kind of control what these samples mean. So for example, you can add, if one of these latent variables corresponds to whether or not the person is smiling, then you can sort of like generate images with the properties that you want. You can, add or remove eyeglasses, things like that, right? Now, the fact that the problem is that we really don't know how to set up this kind of probabilistic model because we don't know how to specify what's the conditional probability of x given the value of one of these latent variables. And so what you actually do in practice is that you turn this kind of principal model that we had before into something flexible, where we're going to use one of those neural networks that we mentioned before. And so we're going to define a probabilistic model where there's going to be some latent variable z, which has some simple prior, like some kind of Gaussian distribution or a uniform distribution, something simple. And then that latent variable is transformed by some complicated mapping, some p theta of x given z, which you can think of as some kind of complicated big neural network that takes the value of these latent variables and then transforms them into a natural image. Now, the idea is that then you can try to learn the parameters theta of this neural network so that you essentially try to fit as well as possible some kind of data distribution. The challenge, and so one principal way to do it is to try to choose the parameters of the model, so such that given some training data set, you try to maximize the probability of observing your training data. So you maximize the log likelihood of the data as a function of the parameters of the model. The challenge is that, as I mentioned before, you only get to see the x, you don't get to see the z. And so you don't really, for a given x, for a given image, you don't know the value of those latent variables. And so the challenge, the main sort of like computational problem in fitting these models is that you need to integrate out, you need to marginalize out all the uncertainty. So given an image, you don't know the value of z. So what you have to do is you basically have to integrate out. Here I'm using a sum because I'm thinking of z as being discrete. You could also think of that as some kind of high-dimensional integral where you have to marginalize out this latent variable. And the challenge is that this is generally intractable because you have to compute some kind of high-dimensional integral over this latent space. And not only that, you also have to optimize it as a function of z. But really, the challenge is that you have to solve an inference problem in a high-dimensional space. You have to compute the marginal probability. And so, a lot of work goes into figuring out that, also from my group and from other people, in trying to figure out principled ways to approximate this kind of computation. The other approach that people often use is called generative adversarial networks. It is that perhaps we can try to get around the problem of computing this marginal probability altogether and try to do something where that is sort of likelihood-free, where we don't actually have to evaluate these probabilities at all. And so the idea here is that we're going to have a model with two components. There's going to be a generator, which is just like what we had before, something that takes some noise, transforms it into a sample. And then there's going to be another piece of the model, which is a discriminator, which is, let's say, another neural network, D, that is trying to distinguish between samples produced by your model and samples that come from the true training distribution. And then what you do is you train these two components in an adversarial way. So the discriminator is trying to do as well as it can at distinguishing the two types of samples, and the generator is trying to fool the discriminator. So it's trying to produce samples that are indistinguishable as far as the discriminator is concerned. And so by doing that, you're essentially ending up learning how to imitate the samples that you have in your data. This is also something that works quite well and people are quite excited about. The advantage being that the only thing that you need to do here is to be able to sample from this model, and this is easy. You just sample from a Gaussian, you feed it into your neural network, you get a sample. And so that's easy. It doesn't involve computing probabilities. And so that's why it's likelihood-free, and it kind of gets around the problem of computing this integral. The kind of challenge with all of these models, I mean, they are exciting because they work purely from raw data. You don't need to provide any labels. You don't need to provide any supervision. It's kind of, sometimes they work, sometimes they don't. So what I'm going to discuss in this talk, there are several ways that we've been thinking about kind of using some amounts of prior knowledge to make sure that these latent variables actually have the meanings that we want, and that also to make sort of these models more sample efficient, so that you need less data to be able to train them. So let's think about, we're going to just as a starting point, let's think about the problem of imitation learning. Just as a brief introduction, reinforcement learning is this really exciting field of AI and machine learning that has received a lot of attention recently. The idea is that you have an agent interacting with an environment and is trying to achieve high rewards. Maybe it's playing this video game, or playing Go, or driving a self-driving car. And the challenge is that you basically have to learn how to map high-dimensional observation of the state, maybe like a raw screenshot of the game, into meaningful actions that will give you high performance, where high performance is measured in terms of high reward or low cost. So if you're thinking about something like the game of Go, basically you just want to find policies such that you interact with the environment, and at the end of the game you win. If you think about Pong up there, then the goal is just to maximize the score in the game. So in some cases this is easy to do, but there are cases where specifying the reward function is pretty hard. So if you think about what reward function should you use in order to learn in order to drive, say a car, right? You need to move forward, but you don't want to move too fast. You don't want to run into other cars. And so specifying the reward function is really hard in some cases. And so an alternative approach to imitation learning is called imitation learning. And that is that instead of trying to maximize some given reward, what you can do is you can try to essentially learn what's the reward function by looking at what an agent, an expert person does when trying to solve the task. So you might observe somebody playing Pong, or you might observe somebody driving the car in the driving simulator, and the goal is to figure out a policy that will generate a behavior that is similar to the one that you've used for training the model. And so this has been studied before. There are several existing approaches to do that, but our approach was to view this problem as a generative latent variable model. At the end of the day, what we're trying to do is we're trying to find a policy, which is a mapping from states to actions. In this case, it's a randomized policy, such that when you couple it with the environment, which could be a simulator or could be the real world, it's going to produce a sequence of states and actions that are going to be indistinguishable from the ones given to you by the expert. And so the framework that we propose to do this is an extension to the generative adversarial networks that I had before. The idea is that we're basically going to introduce some prior knowledge into the way the data is generated by the model. Before, remember, we were just taking noise, mapping it through a neural network and outputting data that was supposed to be indistinguishable from the true one. Instead, what we're going to do next is we're going to actually introduce some black box, which is the simulator, which is the environment, and we're going to ask that this differentiable function that we're trying to learn, when coupled with the given environment, it produces samples that are indistinguishable from the ones given by the expert. So this is a way of introducing prior knowledge because this differentiable function doesn't have to do the entire job by itself. It doesn't need to learn how to map random noise to complicated images and states and action that would be crazy, but it's actually taking into account the fact that we have this simulator and we should use it. We have this prior knowledge about how the system works, and so we can couple it, sort of like combining a data-driven part with something that is based on a more principled kind of physics-based simulator. Yeah. The bias. Mm-hmm. Oh, yeah. So it doesn't go beyond what it sees. So it's going to copy, it's going to imitate what it sees from the training data, but it's supposed to generalize. So it's not just going to copy it and just output exactly what you fit in. The nice thing, let's say if you're trying to learn how to drive, you're going to have to figure out how to generalize, even though you haven't seen exactly the situation before, because there's just so much variety that you're going to have to be able to generalize. Like one of the things we were doing was to train during, the simulator you can play around with like the day of, you can do it during day and during night. You can change the shape of the track. And so what we try to do is we train on one track and then test on other tracks, or train during day, test during night. And I'll show how we can also like even use different experts that drive in different ways, and we can sort of like try to understand what's the variation in the data. All right. So now the question here is that training this model is hard. The reason is that before we had some kind of single differentiable function from here to here, and so you could sort of like compute a gradient with respect to all the parameters, and it's relatively easy to train. But now we have this black box that is something we cannot change. We don't know how it works, and so you cannot just backpropagate the error through that piece of the model. It turns out that there are some ways around it, basically using reinforcement learning kind of techniques. It turns out that we actually have to use some pretty fancy reinforcement learning techniques where you need to look at the information geometry of the problem. So you really need to look at, go beyond sort of like natural Euclidean geometry. But I'm not going to go into much into that. It turns out that you can actually solve that kind of optimization problem. And it works quite well. This is that example that I mentioned before, where we learn how to imitate these behaviors. And what's exciting here is that, I think that was a question raised earlier, is that we can do this from raw visual inputs. So the system here needs to figure out, just by looking at a few frames, it needs to figure out what's relevant in terms of like, recognizing other cars, not going off the road, recognizing how to, and also learn how to map these states into actions in a way that leads to a behavior that is pretty good. Like it needs to learn how to pass other cars, how to not go off the road, how to not to crash, and it's able to do it by essentially just imitating the behavior. So here we're seeing what the policy that we learn does when we run it coupled with the environment. It's the same as what we had before when I was generating samples and I was asking you, are they real or not? This would be the equivalent to that. So we're basically generating samples from the model, and the question would be, is this a human driving or is this the computer driving? And it's doing pretty well. It's kind of indistinguishable. Yeah, this is the computer driving. It's imitating how the driver is actually driving, and it turns out that it's actually trickier. Like you actually have to use a joystick to do it. Or if you just do it with the keyboard, it's too choppy, and then the imitation, it learns how to do some really choppy driving. And so there are some subtleties there. At some point, it even learned, like for some reason, like the optimization wasn't working, and it didn't figure out that it could brake. And so it learned how to brake by basically steering and using the friction to slow down. So there are some interesting things that you can see. There are videos. We have the videos of those failure modes, I think, on YouTube somewhere. Yeah. So it learns it by imitation. I mean, I guess one way you could do it is you could introduce some penalty. I guess you could always add a reward function, but then that would sort of defeat the purpose of doing it from imitation. But yeah, I mean, I don't think this is the solution to the problem. It's a cool demonstration that you can learn how to imitate complex behaviors purely from raw visual inputs, right? Yeah. Yeah. I think it's 3 frames, yeah. I don't know. We only tested it based on what the simulator spits out. Yeah. All right. Now these are some other examples where we learn how to control these robots in the simulated environment. Here the goal is to learn how to control all the joints of this humanoid robot in a way that it imitates the way basically humans walk. And well, it doesn't do a great job, but it kind of got the most of what it should be doing. Now, the interesting thing that we can start to do once we have such a probabilistic model is we can try to understand what's the meaning of these latent variables. The idea is that perhaps we can understand whether these latent variables have some kind of semantically meaningful latent structure. The idea is that, remember what we were doing before, when we had the images, we were able to kind of understand, we were able to discover some latent variables. Remember, those are the Z's that sort of had some kind of semantic meaning. They correspond to smiling or eyeglasses, things like that. And the question was to see whether we can do something like that on behavioral data. If you just show a lot of examples of different kinds of behaviors, what would these latent variables correspond to? Or is there a way to kind of have latent variables that have some kind of semantic meaning? Is there some kind of latent structure in this high-dimensional space of demonstrations provided by the expert? So that's something we can do using some mutual information stuff that I'm not going to talk about, but here are some examples where we've learned how to disentangle two kinds of driving behaviors, one that has a preference towards passing on the left and one that has a preference towards passing on the right. So depending on how you set the variable, it does two kind of different things. So my hope here was to actually be able to kind of learn a latent variable that kind of corresponds to how aggressive you're driving, and that didn't quite work out, but because I guess it's too subtle or somehow it didn't learn it. But this is a much sort of like stronger kind of distinction between these kinds of behaviors, and it was able to learn how to separate them, and one of these latent variables actually ended up corresponding to this behavior. We've also applied these kind of techniques to more, perhaps more concrete and important problems. We've been studying how how people in some parts of Africa are affected by climate change, by studying how they value different kinds of resources, water and pasture land. So we have like a lot of GPS data on how they've been moving around Ethiopia for several years. And we've been using like remote sensing data in combination with this kind of data to try to understand what kind of preferences they have and figure out a way to basically price insurance products. But I'm not going to talk about that much. Instead, I'm going to talk about some other applications in the sustainability space towards the second half of the talk. How much time do I have? Maybe another half an hour or something? Half an hour, okay. So maybe I'll talk briefly about this. One reasonable way to incorporate supervision into these kind of systems is to use labels. So let's say that you have a bunch of images corresponding to digits, and that for some of them, let's say that you know that this corresponds to a 5 and this corresponds to a 0. So the classic way you would do it is by training some kind of neural network to map the inputs to the outputs. And this is called discriminative learning. Now let's say that you also have a lot of other images for which you don't have the corresponding label. Because labeling costs, and just the images instead are kind of free. So what you can do is, you can just throw them away, just use the labeled component of your data, and that's it. The other thing you can do is you can use all your data and just train up one of these generative models that we've been talking about. You try to learn some kind of latent representation that is sort of able to generate the data, but then the question is, you're not going to be able to use the labels that you have. And so one thing that we did was to try to see whether you can combine discriminative models with generative models. And one simple attempt that you could try is to do something like this. You basically train two separate models. You train one model that goes from the X to the Y to the label, and some kind of neural network, and then you train one model that sort of learns how to, a latent variable model for your images. The problem here is that kind of the two models are separate. So if you were to try to optimize them, you would just separately optimize the two components, and you wouldn't be really doing anything interesting because there is no way for the two components to kind of interact with each other. So the simple solution that we had in this paper that we presented over the summer was to actually couple them through this latent space Z. And so that basically we're forcing the latent representation to be good enough to be able to explain the variation that you see in the data, but at the same time, these latent variables should also be useful for predicting the labels on the data points for which you have labels. And so this turns out to work really, really well for semi-supervised learning. Here, the setting is that you have a lot of data, but very few labels. Let's say that you have MNIST here, and you have a lot of images, but only, say, 100 labels. And it turns out that by using this combination of the two approaches, you can get something like 0.9% accuracy. So it gets less than 1% of the classifications wrong, just using 100 labels. So a very, very small number of examples are sufficient to learn how to solve the task because it's using the generative part to kind of learn what's the latent structure of the data. If you use SVHN, where we're trying to classify house number, street view house numbers. Street view house numbers. These are house numbers from the street view images. So you're trying to basically classify them into digits again. These ones are color. It's a little bit more challenging. And again, we were able to get state-of-the-art results here on something like 4% accuracy with a relatively small number of labels. I don't think so. All right. Now let's talk briefly about another way of incorporating prior knowledge, which is to use physics and domain knowledge. Let's say that you want to learn how to map videos. Let's say you have like a video of a person throwing an object in the air, and you want to learn how to track that object. And so you can sort of think of this as another of these latent variable models, where there is some data that you get to see, like the frames in the video, and there is some latent variable corresponding to the height of the pillow over time, that red pillow here that the person is throwing, right? Now, we don't know, we don't have any labels, so we don't know the height of the pillow. But one thing we know is that we know elementary physics. We know that the trajectory of the pillow has to be a parabola, right? This is just Newton's law. We know that if you throw a pillow, that the trajectory should form a parabola over time. And so what we can do is we can try to use this knowledge to learn how to recognize and track the pillow. The idea is that we're going to train a model that maps images to the height of the object in each image. And even though we don't know the value of that thing, we know that the outputs, if the model is right, it has to be a parabola, right? Even though we don't know what are the precise values, we don't have any label here, we know that the structure has to be consistent with the elementary kind of laws of physics. And so it turns out that if you try to train a system to solve this task, even without any label, just purely based on this kind of high-level description of the kind of things you're trying to discover in your data, which is just this simple equation, you can learn to track a pillow with something like 90% correlation without any labels. Now, this was sort of like the toy example we started with. You can actually apply it to more challenging tasks, like learning how to track a person. Here, the prior knowledge was that we know that people tend to move at relatively constant speed. And so again, we were able to learn how to track people in videos with something like 95% correlation with the true position without using any label. And you can actually apply this to using more, not just prior knowledge in the form of equations coming, say, from physics, but you can also use domain knowledge expressing kind of logical properties of the things you're looking for. This is a synthetic example where we were trying to see whether we can learn how to recognize these video game characters like Peach and Mario. And we said, well, we're not going to provide any example of what Peach looks like or what Mario looks like. But what we're going to tell the system is that whenever Peach is in an image, then Mario is also there, but not vice versa. So there could be images where there is Mario, but there is no Peach. Then there are a bunch of other confounding characters. There are different backgrounds, and there are rotations. There are kind of all other things, a bunch of other things that we're doing to try to make the job of the model harder. And it turns out that this actually fairly weak kind of supervision, where we're just saying the only thing that it needs to know is that look for an entity A such that whenever A is present, B is also present, is actually sufficient for learning how to recognize Peach and Mario. Here you can see basically the way to think of this is that when the neural network is saying that Peach is present, it's sort of like looking at these pixels down here. And when it says that Mario is present, it's sort of looking at the pixels up here. So it's kind of learn how to recognize these characters purely from this sort of like very weak form of supervision. Now, one issue with this approach is that you need to specify these constraints manually, which could be problematic. And so one thing that we were looking at is whether we can use simulators to provide prior knowledge, like what we had before. So let's say that you want to learn how to track a pendulum, and let's say that you don't know physics well enough to write down an equation for the motion of the pendulum. But let's say that you have access to a simulator that can provide trajectories that are consistent with the laws of physics. And so what we can do is we can use an approach similar to the adversarial training that we had before, where we're basically going to train our neural network to map video frames into the position of the ball. And even though we don't have any label, we're going to ask the neural network to produce outputs that are consistent with the ones produced by the simulator. And the way we measure consistency is by having a discriminator, like what we had before, that is trying to distinguish between the fake data that we produce out here and the real data that is produced by the simulator. And so these two play a game where this guy up here is just trying to do as well as it can at distinguishing the two things, and this generator here is just trying to fool the discriminator. And by playing this game, it learns how to solve the task. You can learn how to track a pendulum, which is maybe not too interesting, but you can also learn how to do some simple motion capture tasks. Here, writing down the equations corresponding to the constraints that you have on the joint positions of the joints of a human skeleton is pretty complicated. I mean, there is going to be some constraints like the distance between this joint and this joint is sort of like fixed, cannot change. But it's hard to write down equations, but you can relatively easily get a simulator, and you can learn again how to do these kind of tasks without any labels. All right. Questions on this part before I move on to some applications? Yes. Yeah. So we don't just know the height. We were working on a simplified. What's the question? Only the height, yes. So is the question how we evaluate? So we actually label it by hand. Well, if you know the height, then at least you know something, right? Because we're assuming that the speed is constant, the velocity on the other dimension is constant, so you can essentially track it. Yeah. Yeah. So you can, it's shown, I guess, on this picture here. Is that the question? Like whether we can? So we have basically, the way this works, maybe I didn't explain it very clearly, is that we have a simulator producing realistic kind of joint positions of the skeleton, and then the neural network is trained to produce outputs just looking at the videos that are consistent with that. And that turns out to be sufficient to kind of constrain the tracker to do a good job. And it's empirical. I think we don't have any proof that this will always work. It did work in these cases. You do need a little bit of regularization to make it work, but it did in this case. Yeah. We cannot recognize pillows versus non-pillows. Yeah, it's a simplified kind of relatively toy example where we wanted to see is physics. Can you do something just by knowing elementary physics? Could be any other object. Yeah, it doesn't know how to distinguish. We did it with basketballs. It doesn't know how to distinguish between a pillow and a basketball. Yeah.
I'm having trouble reconciling the two components of the top right picture.
Uh-huh.
Stick figure seems to be moving not the way lines work.
Yeah, it's definitely not perfect. You can quantify, there are some known metric, precision, a K that people use, and you can get decent numbers. This is definitely not perfect. Like,
what is the accomplishment?
well, that you can get if you look at the quantitative metrics that people use, basically how far the joints are to the true. People have labeled these things, so you can actually compare how well you're doing, and you can get pretty good numbers without using labels. So there's no training, just basically trying to imitate something that the simulator is producing. Yeah. It's a good question. So it's a way of incorporating prior knowledge. I would say that the main difference is that it's done likelihood free. So the problem is that it would be very hard. We want to work with complex models where evaluating probabilities is really hard. And so we are using these relatively new techniques that are likelihood free. But I agree, yeah, that would be the principle. If we had infinite computation, I would definitely go that way, and I would do it the Bayesian way. It's just that it doesn't scale, basically. Yeah. Yeah, so it's in the paper. You can use a combination. You can do purely without any label. Like the examples I showed before, these are done without any label data. This one, you can actually plug in a little bit of label data, and then you can sort of see how much the unlabeled data helps. Yeah. Mm-hmm. Yeah, I guess I don't remember the numbers off the top of my head, but we did these experiments where we sort of evaluate how much labeled and unlabeled data you use and how the performance changes. But unlabeled data is pretty cheap to get. So it's usually not a big concern. All right, so let me talk about something different in the second part of the talk on how we're using these kind of techniques to solve more important problems than classifying digits and dealing with these kind of issues. And in particular, how we can use AI and machine learning to deal with the big societal challenges like poverty eradication or ending hunger and climate change and these kind of things. So one of the big issues that you encounter whenever you talk to people that work in these kind of domains is that there is this big data divide between developed countries that are sort of like flooded with data and developing countries that are literally suffering from data drought. Like if you see in this graphic from the UN, this is showing the availability of the various indicators that one would need in order to be able to track these sustainable development goals that were approved by the United Nations a couple of years ago. And it turns out that a lot of the data is missing. About half of the indicators that we would need to figure out how well we're doing towards ending extreme poverty or hunger are actually missing. And so one of the things that I've been exploring is whether we can use AI and machine learning techniques in combination with unconventional data sources to try to fill this gap. And so to give you an example, let's look at poverty eradication. This is the #1 goal on this 2030 development agenda. And the kind of data that we have about poverty is super scarce. This is a map of the African continent, and it's showing the availability of nationally representative surveys in the decade from 2000 to 2010. And you can see that many of the countries are white or very light blue, meaning that there is no data available for that country for an entire decade. And so, as you can expect, with this kind of data, it's really hard to track progress, hard to do research, how to implement, figure out whether policies are working or not, and things like that. So one thing that we tried to do was to see whether we can use high-resolution satellite images to kind of predict various kinds of poverty measures. The good thing is that satellite images are getting better and better, cheaper and cheaper. There's a lot of private companies that are entering the market that are providing high-resolution images at a fraction of the cost that they had a few years ago. And you can clearly see a lot of information in these images. You can see information about infrastructure, about economic activities, cars, roads, and so forth. And so our question was whether we can train some kind of machine learning model to go from the images, which are basically available in every corner of the world, and they are cheap and they are updated frequently, and come up with these kind of poverty maps. And so one model that we use is actually very similar to the one I had before with the parabola. The idea is that we want to predict something that is over space and time. And we know that this kind of poverty measures that we want to predict are actually very highly spatially correlated. So if you take two locations that are close to each other, they're more likely to have similar values in this poverty, the various kinds of poverty metrics that we considered. And so one thing we can do is you can train some neural network that takes as input a high-resolution image of various locations, and it maps it into some kind of poverty value estimate. And then you can use a Gaussian process to essentially enforce the spatial correlation. And you can think of this as a sort of like a soft version of the constraint that it has to form a parabola that is sort of enforcing the fact that locations that are close to each other should have a similar value. But the idea is very similar to the parabola I had before. Yeah. It's the same network, yeah. It would actually work pretty well in North Korea, I would say, probably because we also use nighttime light information, and it's actually completely dark at night. So I don't know if I have it in this slide deck, but I actually use it as an example of where it would work pretty well, because you can see South Korea looks like an island if you look at the Earth from space, completely disconnected, and you just see Pyongyang, just a little bit of light at night. Yeah. Yeah. Yep. So maybe it wasn't clear. This is not going to be completely unsupervised. This is semi-supervised. So we're going to use labels and unlabeled data. Yeah. So it wouldn't work without labels here. All right. So it turns out that this works quite well. This is how, if you try to predict just from, we take some survey data from various organizations, and then we look at the various locations, we take imagery, we fed it into the model, and we try to predict how poor or rich each location is, and then we compare that with the ground truth. So we pretend we don't have that number, we predict it, and then we see how well we do. And you can see the model is not perfect, but it's capturing about 70% of the variation in the data in Uganda. That was for 2011. And so clearly, I mean, there's going to be a lot of stuff that you just cannot see from the images. You cannot see inside people's houses. But you know, it's doing a reasonably good job at predicting this. It's actually the best that's available at the moment. It's you know, my colleagues in the social sciences couldn't believe that this was possible. This is really like for machine learning standards, this might not be super. You know, an R square of 79 or 0.69 is not maybe the best, but in the social sciences, in this development area, this is mind blowing. These are clusters as defined by the World Bank surveys. So this work got a lot of attention. Bill Gates was tweeting about this. It was mentioned on the White House report on the future of AI. We've been collaborating a lot with several NGOs and government organizations. Like the World Bank has implemented this, and they are using it to come up with estimates for different parts of the world where they cannot send people to collect surveys. We generated a map of Somalia for them a couple of months ago. It's a country where they cannot send survey takers. They would get just kidnapped or killed. And so, you know, lots of excitement about this. That's something that was actually selected last year by Scientific American as one of the 10 ideas that will change the world. And so that was really exciting. And you know, we're really looking forward to using these kind of models for helping out government organizations, NGOs, and also to support scientific research. Now, yeah. So we have a few thousand, several thousands labels, and essentially an infinite amount of unlabeled data. Because we have images for every part of the world, so you can fit in. We use 500,000 probably. So you can get as many as you want, basically. Yeah. We didn't just apply this to poverty. We also looked at hunger-related measures, like food security measures. We tried to see whether we can use cheap, unconventional data sources from satellites. We're also starting to look into social media, but for now, let's say satellites to kind of predict food security measures. In particular, as a starting point, we looked at agricultural productivity. We used a model very similar to what I had before, a deep Gaussian process with a neural network and a Gaussian process on top. So as a first step, we looked at agricultural productivity, as I mentioned. And this is what the model does if you apply it to the US. So here we were trying to predict from space soybean production in the US at a county level. So what the model is doing here is basically every week it gets new images from the satellites. It's fed into the model, and it's used to update its prediction on how productive that county will be in the US. And it's doing it from space, so it's learning how to track basically plant the growth and health from space. It's doing, and you see how basically it's updating the predictions as it gets more and more data. It's doing, it did quite well. This work actually won the World Bank Innovation Challenge a few months ago among several hundred submissions. And I can show you that it's actually doing better than what USDA can do at the moment. So here we try to see how well the model does historically if you were to train on data up to a certain year and then make predictions on the following year. And then we try to see how well it did in the past. And this is showing the percent error that you get in different years. And you can see that if you try to make predictions in July, then the average error is about 5%. And USDA does not even try to make forecasts in July. The first forecasts from USDA, historically, this is the kind of error that they have. So about 3.92% on average. And our model is actually getting 3.3% historically, so slightly better than USDA. And in September, we still do slightly better. And then in In October, with SDA, that's better. But what's exciting here is that we only use satellite images. So again, it's very scalable. You can apply it potentially in every part of the world. We're trying to apply it now in South America, African countries. And so pretty excited about the possibility of scaling this up basically on the entire world scale. Well, you can see the numbers here. It's not perfect, but it is doing pretty well. Finally, maybe I'll mention a little bit of my work on using AI and machine learning for energy research. The idea is that there is currently a lot of bottlenecks in the way people do experiments, especially in material science, from using their domain knowledge to design experiments, getting data from high-throughput experiments, analyzing the data, and going back. And one of my research goals is to use AI and machine learning to kind of speed up the whole discovery process. Hopefully, at some point, get to the stage where we can do research and sort of like close the loop and have a completely automatic system that does the experiments, collect the data, designs new experiments. We've done a little bit of work in the data analysis. This is another domain where you can use machine learning and physics to kind of try to understand chemical properties of materials, but let me skip about that. Let me talk a little bit about how you can use probabilistic models to also guide optimizations and make decisions in a smart way. Turns out that we've been working with physicists up at SLAC, the Stanford Linear Accelerator. They have this wonderful X-ray laser called LCLS. It's like a 2-kilometer machine, $400 million. This is 280. It's below 280. You pass it if you go. This is Sand Hill, and this is LCLS. It's a very expensive machine. It costs $1,000 per minute to run experiments. It's oversubscribed by a factor of 5 or 6. And it turns out that every time they do an experiment, there are technicians that are basically controlling these giant magnets to get good performance in the beam. And so what we were trying to see was whether we can use AI and machine learning to speed up this process and potentially even get better performance from the machine. And so what we did is we used one of these probabilistic models that is kind of trying to understand, try to learn how the setting of these magnets of these parameters translate into performance of the beam. Again, it's combining data plus physics-based models. But you can see here an experiment that we ran live at SLAC, where we're actually controlling all these magnets. And basically, the way it works is that it has a probabilistic model of how well different choices of the parameters will work. And it will try to balance exploration and exploitation. So we'll try to find choices of these parameters that will give good performance, but at the same time, it's trying to understand how the machine works. And so it's keeping an uncertainty measure of how, which kinds of parameters you should try next to get a sense of how the machine works. And it did really well, about 4 times faster and better than human operators, and about 2 times better than gradient descent. So they're pretty excited about this. They want to apply these kind of techniques to other accelerators. And so, yeah, this is another example of kind of domains where you can use data and prior knowledge, in this case, to do better science.
What are those images showing?
Yeah, so here is basically the prediction. This is showing as the model acquires new data, how it's changing the model, essentially, what it's predicting. So this is predicting as a function of, just because we're using like 20 or 30 parameters. This is just showing a slice of 2 parameters. And it's showing as a function of these 2 parameters where the model thinks that there's going to be improvement in the performance. And so you can see that it will move around and then sort of like zoom in to points that it thinks are high performance. This is just a visualization, yeah. Oh, these are actually two of the magnets. It's just one slice. Yeah. Right. So just another example of how you can combine AI and physics to do fun stuff. Yeah. So I think I'm out of time, so maybe I'll skip this. This is another application that predicts. This is really recent, as of like last week. using these kind of latent variable models to guide protein optimization. You can learn how to map sequences of amino acids into one of these latent spaces, and then you can use the latent space to kind of predict how well different variants of these proteins will work, and then you can use it to synthesize new proteins that we think are going to have good performance using, again, a Bayesian optimization style technique that is basically using a probabilistic model for the data, and it's guiding it. We're using it to guide the design of new proteins in this case. So we're sort of like finding a way to find a continuous latent variable. This would be the Z variable representation of different amino acid sequences, and then we map those to some kind of properties of these proteins that we care about, like the fluorescence, and then you can sort of move around in this space, find a point that we think is going to have high fluorescence values, and then we can map it back using this mapping from latent variables to data. Before it was images, now it's amino acid sequences, and it seems to be working quite well. This is an example of the kind of proteins that you get using this approach. This is still not published. It's work in progress, but it's just showing another kind of ways in which you can use AI and data science to help out in the physical sciences. And I think I'm out of time. Some acknowledgements to the various funding agencies and all the students that did all the work. And thank you.
Thank you very much. I think we have time for maybe 10, 15 minutes if you have any questions.
Yeah. Yeah. So latent variables just means variables that are not observed. They're latent in the sense that you don't see their value in the data. They're missing values. You could think of them that way. A Gaussian process is just a collection of random variables that are jointly Gaussian distributed. And we're using that as a way to model essentially a sequence of continuous random variables that might potentially be correlated over space or time or some other kind of strange latent representation. What was the other question? I guess if you think about, there is a probabilistic interpretation of principal component analysis in which the principal components would correspond to latent variables. And also ICA, if you think about independent component analysis, there would be another probabilistic model in which the independent components are indeed, you can think of them as latent variables. The difference is that those are sort of like linear models. These models are nonlinear. Yeah, so that's a good question. So the reason we use Gaussian distributions is that they're convenient to handle and they're tractable. As soon as the distributions are not Gaussian, then it becomes a little bit more problematic. Something we use is mixture of Gaussians, which is still kind of relatively tractable. But a lot of the times yeah, essentially, yeah. So I should mention that even in the crop yield, it's a semi-supervised setting, so it's not purely unsupervised. So we do have labels. We use the historical data and unlabeled data at the same time. Yeah, I would imagine that there is probably a way to bias it. I'm not sure why you would want to do it, but I would imagine that you could force it to essentially take some value. If you know that you'd rather have small values than larger ones, you could add a penalty and kind of try to force it to do it that way. I'm not sure how it would play with the other parts of the objective, but it's probably doable. Yeah. So we're doing some of that. So we're trying to do speed up quantum computations like DFTs. So we're working on predicting material properties. And so my colleagues are spending we have this very expensive quantum computations that take maybe several days. And they have essentially an infinite space of possible candidate materials that they would like to evaluate. And so we're using very similar ideas like Bayesian optimization style things to basically encode the materials into a latent space and then use the latent space to predict the properties that we care about and then suggest new materials that they should try first to kind of prioritize the way they do their computational experiments. Well, I wouldn't say that. I don't think we can do that. I think it's just a way to try to essentially use these very flexible kind of models like neural networks and kind of fitting them to some, at the end of the day, this quantum computation is going to be some complicated mapping from some inputs to some outputs. And what we're doing is we're just trying to fit some function to that. It's just regression at the end of the day. And then we're plus some probability distributions that we can use to kind of get a sense of how uncertain our predictions are. So that, and in some cases, even if the model is not good, is not great, but it's good enough that it can tell us, just don't do this experiment. It's going to be terrible, so just avoid doing it. But then there are cases where you really need an accurate answer, and this is not going to work. Yeah. Yeah, so in terms of training time, it's not too bad. It's probably around 12 hours on a Titan X GPU. So something you can do on your home computer with a $1,000 GPU, you can do it. More data would definitely help. I'm pretty sure that you can just make the model larger and throw more data data, and it would work. It would work better. Especially higher resolution images, I think that would help, or more frequent. We're working with Planet, and they're getting images of basically, they're getting to the point where they can get images of the whole world every day at 2-3 meter resolution. And so with that kind of data, you can start, couple it with fancy machine learning AI techniques, you can start to think about, you can track what's going on at a global scale with pretty high temporal and spatial resolution. Yeah. Oh yeah. Well, that's always the problem. It's not, with this kind of models, overfitting is really, really easy. It's actually the first thing I tell the students: just try to make sure you can overfit. That's a good sign if you can do it. And then just to make sure you don't have bugs. But then these are always, I'm always reporting held out predictions. So accuracy, say, on held out predictions. So we are trying to be as careful as possible in terms of having train and validation and test splits, and always reporting at the end on some data that we haven't seen before. Yeah. So we always evaluate on sort of unseen data, or we're trying to do something as close as possible to that. Let's say in the poverty prediction project, what we did was to say, well, what happens if you were to train the model on 4 countries and then test it on a different one? So we try all kinds of experiments to make sure that the numbers that we report should be more or less the ones you would expect if you were to really use the model in the real world. Yeah. Uh-huh. Yeah, so there are ways in which you can sort of one of the innovations was like a way to kind of force the model to, to kind of find these entangled representations. But it's a tricky problem. Like it's not easy to do. Even what disentangled really means is not clear. But so a lot of the work that we've been doing is trying to make sure that these latent variables actually mean something physical or something that is consistent with human judgment. So one way we do it is by basically adding these mutual information penalties that say that this variable should have very high mutual information with the image, and that is kind of forcing it to be sort of like the most significant bit. But that's not always the right choice, and it doesn't always work. Yeah. It's a big question. It's a hard question also. Like say in the context of the poverty prediction, what we did was to try to visualize the filters, and we had a pretty good sense of the kind of things the model is looking for. Like it was reasonable stuff like roads, houses. There was even a filter that was looking for swimming pools. So that was pretty convincing that it was doing something reasonable. It figured out that if there are swimming pools in this area, it's probably, but it was not by inspection, yeah. Yeah, so that's still basically the state of the art, I think, as far as I know.
I think we go for the last question.
Yeah, I mean, I don't think they are just memorizing the pictures. They're definitely doing something something else because just because of the fact that these models do work well on held out data, but they're definitely not solving the problem the way we are solving it. They are fitting to strange kind of and imperceptible, potentially even patterns and trends in the data that we don't necessarily see. So they're definitely not solving the problem the way we think they would. And there are numerous examples on how you can even, just some of the work we do is trying to understand these adversarial examples. Like it turns out that if you change an image by an imperceptible amount, a few pixels, then you can completely change the prediction made by the network. And that is kind of telling us that they're not, obviously not understanding what's going on in the scene, in the images. So, but I don't think they're just memorizing. It's just solving the problem in a different way. I'm not sure. My intuition is that they are not memorizing. And I think if they were memorizing, they would not generalize well on test data. So that's my argument for why I don't think they are just memorizing data. Yeah.
Thank you, Professor Ermon, for a very interesting talk. Thank you all for attending. See you next time.